Alright, hell yeah. So we're going to revisit this problem, you know what I mean, because I took 4 hours on this one, and you know what I mean, and someone's like, hey, did you have a mistake somewhere maybe? And probably, but I probably fixed it towards the end, but no one's going to watch that 4-hour movie. So I was just, for myself, you know what I mean, could I be able to answer this question, you know, fairly easily? So this ball is going to be hit, it's a golfing shot, it's going to be hit at a 45-degree angle, but we don't know the initial velocity, bummer, you know what I mean? But we do know that the ball, and we're just going to assume it's like a horizontal course, because that was the other thing. If you have an elevation drop, we covered that at the end. That was kind of fascinating. But we're going to get a range of 285 meters. So now the two equations that we use is that, hey, we derive them from acceleration in the y is negative 9.8. And so our velocity in the y is negative 9.8 times t if we integrate. And we're going to say at time t is equal to 0, we have an initial velocity of v initial sine 48. And then we have a position in the y of negative 4.9 t squared plus v initial sine 48 t, or just, this is just theta, you know what I mean? But for our problem it's 48, so we're good to go. That's not, that variable is not changing. Hell yeah. Now at time t, this is our origin 0, 0. And then at time final, you know what I mean, right there, we're going to be at some x, but hell yeah, we're going to be back to 0. Okay, so those are those equations. Acceleration in the x is 0, so velocity in the x is not a function of time, it's just the initial velocity in the x. V initial cosine 48. And then position in the x is v initial cosine 48 t. So now what we know is that at time final we're going to have this x, cool, but we can also solve for that time because our ball is going to hit the ground again. And so we just throw in 0 here, and that's an easy one, negative 4.9 t squared plus v initial sine 48 t, and then we factor out a t. So we go t negative 4.9 t plus v initial sine 48. And now if this side is equal to 0, either side equal to 0, we're good to go. But the time 0 is that point, the time whatever comes here. So we're going to set this equal to 0. So basically we got 4.9 t is equal to v initial sine 48. And so then t is v initial sine 48 divided by 4.9. And whoa. Yeah. So we still have two unknowns. We still don't know what the initial velocity is. Bummer. But this is the time. This is time final. You know what I mean? So this is, when we shove this into this equation, that'll give us that 285. So this equation becomes 285 is equal to v initial cosine 48. And now we shove this in. V initial sine 48 divided by 4.9. So hell yeah. So now we can rearrange and solve for v initial. So that's going to be 285 times 4.9 divided by cosine 48 sine 48, and then we have that's going to be equal to v squared, so the square root of this is v initial. Alright, so hell yeah, so we got 285 times 4.9 divided by cosine 48 divided by sine 48, and then square root of that, and we get a velocity of initial of 52.99 meters per second. And like I said, times 2.25, that's 120 miles per hour. That's what I was like, hey, it's like terminal velocity. But anyway, but then the person said, well, because I said something about miles per hour, he thought I changed things to miles per hour, and I might have. I'm not going to rewatch my video, so might as well just make another video and get there faster. But I was just surprised that what was I surprised at? I was surprised at the loft of a golf ball. So now we put this back into either of the equations and solve for time final. So this one would say time final is x divided by v initial cosine 48. And then so this is 285. So we got 285. Oh, I'm gonna store. Maybe that's where I got bummed up. You know, maybe I stored this as alpha v. and my problem was just off from there. Maybe I'm making the same mistake. So no, this is the velocity in meters per second. We're going to store that as alpha v, and so now we got alpha v. So now we got 285 divided by alpha v divided by cosine 48. And so we get a time of 8 seconds, 8.04 seconds. And yeah, and maybe, well, if I divided by a bigger number, we would get less time. So, is that true? I guess so. Yeah. Divided. Yeah. Anyway. So here we go. So there's the time. We can recheck the time here because we can say what can we throw into here? Well, we can make this a quadratic, and we can go 0 is equal to negative 4.9 x squared. We're going to solve for time plus alpha v sine 48 alpha t, and that's the x value. We're going to zoom 6 that, and we're going to have time. Well, oh shoot, no, the time will come right down at 8 seconds. Perfect. And then we don't even have to, you know what I mean? We could value that 8 and then 0 it, left bound, right bound 0, and we get 8.04 seconds. So sweet. So I'm going to store that as alpha t. So this is our time, and we have our velocity initial. What I was fascinated in is if you have something that has a velocity of 50. Let's say you just have this velocity initial, but you shoot it straight up. I always ask those questions. At 50 meters per second, how long is this ball going to be in flight max? Well, this is super easy if we just treat acceleration as 10. You know what I mean? How we say 9.8. That even is a little confusing. If you just say, hey, it's average of 10, and what does this mean? It's negative 10 meters per second. And if you write it like this, our velocity is going to change by negative 10 meters per second every second. And if you forget about the negative, you can obviously, well, it's all going to slow down on the way up. So if we have 50 meters per second, every second, this thing is going to go from 50 to 40 to 30 to 20 to 10 to 0. Cool. Now it's stalled. And how many seconds was that? 50 to 40 to 30 to 20 to 10 to 0. It's 5 seconds. So visually and obviously, yeah, if we have 50 meters per second straight up, it's going to be 5 seconds of till the top, and then by symmetry 5 seconds. So our time for a vertical thing would be approximately 10 seconds. Okay, hell yeah. So now what this problem says is we have the Earth is rotating. And so let's say you were at the North Pole. This problem makes so much sense as if you're at the North Pole and then you just shoot the ball where you thought the hole was. So that's what they're saying. But guess what? The Earth is rotating, let's say that way. And by the time you get there, well, the part of the ground moved over here. You know what I mean? Because you lined it up. It would be like, hey, if I was at the North Pole, had an airport, and I saw that, let's just say you're trying to get to, I don't know, New Zealand. Perfect. You know what I mean? Hell yeah, New Zealand's way the hell down here, and then you're just like, sweet, I know New Zealand's way down there, and so I'm just going to go that direction. But by the time I fly to New Zealand, guess what? New Zealand's probably over there. You know what I mean? So that's what this problem states, and it's a Coriolis problem. You know what I mean? And I get it, but I don't get it, because Coriolis is like, well, the spinning globe, like, stuff shears on it. So air molecules right next to the Earth are traveling at the same speed of the Earth. So like if you look, yeah, that's the fascinating thing. But I get it, because air molecules at the North Pole are just spinning in a friggin' circle and hardly moving. But air molecules over here are hella getting traveled this way. So if those air molecules at some point butt up against these air molecules, now you have a shearing effect. These air molecules are moving faster, these aren't. And so, you set the Coriolis effect into motion. But for our problem, it's a straight, it's like a, you know what I mean? It's like the carnival game. You know what I mean? You have, this is your target, and then guess what? You have a bunch of moving targets, and then they're all moving this way. And so you thought you were aiming at that one, but by the time the BB gets there, you missed. You basically hit right there. And so then this problem, Hell yeah. So then this problem just becomes, well, if you thought you were going to aim there and it took a time for you to shoot, and that we stored that as our calculator t, but we have this velocity, well, so you have meters per second, and now you have some sort of seconds. So what can we do to these two things to find meters? Well, we can multiply. So this velocity times time is going to be, so we're going to have meters per second times that second the ball's in the air, and this is the meters that we're going to miss. And so as long as we can find this velocity, now if we had the golf course to the North Pole, hell yeah, we would just figure out how far we went, and then figure out that circle around the Earth, and we could figure out the speed of that circle. But we're not there. We're at 35 degrees north latitude, and so when we shoot, maybe we're at 35 degrees 00 minutes, but 0.1 seconds. Actually, probably more than, you know what I mean. And then we did that. We figure, well, how far is a second? You know what I mean. And I think a second, I thought it was just like I don't know. Is it a meter? You know, who the hell knows? Who the hell cares? But you're gonna be at a bigger circle. So when the ball lands there, you know what I mean. So in a day, this t moves at a velocity of that circle's path in 1 day. And now we have 365, and that was the thing, because one spin, the velocity of the Earth isn't 360, it isn't 24 hours. It's minus 4 minutes, is because also the Earth is traveling around the sun. I don't want to get into that, but just know that the Earth physically only rotates in 23 hours, 56 minutes and 4 seconds. I think that is what I recall. I'm going to pause the video because that's the next thing that we need. Alright, hell yeah. So we got that. It's exactly 23 hours, 56 minutes, and 4 seconds. You can memorize this, but you don't have to, because you just know that there's 365 revolutions, in one, I mean 366. There's an extra revolution, because what happens is the Earth rotates, but then the Earth rotates. You have the sun over here, and then the Earth is spinning. But then the sun, we're also spinning around the sun. So the second, and we're spinning in the same direction too. So we actually get there faster. You know what I mean? So if I'm here, so if the sun's right here, and you're saying, hey, this is high noon. Well, the time I spin once, I'm already over here. And guess what? You were facing right there, but the time I already spin once, I'm facing this direction, but I'm over here. And guess what high noon is? High noon's right here. You were spinning this way. Do I have this right? Spinning this way and then spinning this way. So here's the sun. You're going to spin once. Pretend that we did that. Cool, you're high noon. As long as we're not going around the sun, yeah, it's going to be 24 hours. But because we rotate over here, well, now this part's high noon. Oh, am I saying this wrong? Oh, no, I don't think I'm saying this wrong, but it's 23 hours and 56 minutes to do this. But then the second we're up here, you actually have to rotate. So this shows you have to rotate another 4 minutes to get to high noon. See that again? So like we're on the Earth, this is the sun, this is high noon. And then you rotate once, say we did that. Cool, now you're high noon. But as long as we're not going around the sun, it's going to be 24 hours. No, I apologize. We're already saying this rotation is 4 minutes less than 24 hours. So cool, we did it in 4 minutes less, but guess what? Now we're over here, and you're not even facing, you have to rotate that much farther to get back to high noon. Holy hell. But that's why it takes you that extra 4 minutes to get to high noon every day, because you're rotating around the sun. You have to take extra time, even though the Earth spins once. But by the time, the Earth always has an extra spin, and by the time you do get around 360, yeah, it's like the Earth spun another time, and it did. Earth spins 366 times on its axis for 365 days going around the sun. All right, holy hell. So, but what we want to know is just the velocity difference. So we need to figure out, and they already spell it out. The radius of these rings is radius times the cosine of that, and we're saying 35. So 35 degrees. Cool. And then so that path length is the circumference is 2 times the diameter, or so holy hell. I love how there's no equation for circumference that actually is visually satisfying, but circumference is pi d, circumference is 2 pi r. So this circumference is going to be 2 pi re cosine 35. So that's the circumference, and then we could figure out, so that's going to be in meters. They say the radius of the Earth is, 6 million meters basically. And so we would want to, that's in meters, we want to find meters per second. And so you have to travel this many, the circumference, in 23 hours, 56 minutes, and 4 seconds. So we're going to go 23 times 3,600, that's how many seconds that is, plus 56 times 60, that's how many seconds that is, plus 4 seconds. So we're going to store that as alpha s, and this is the seconds to rotate. So now we have circumference divided by s in seconds, and this is going to be the velocity at that point. And so, but we just need the velocity difference, so maybe some of this comes out in the wash. So that's our equation for velocity at the T box. Now at the hole, we're going to be at a different radius, and so, man, this is a bummer. I'm actually going to pause the camera because I just want to make a shorter video and then figure out if I got the problem right. Alright, hell yeah, that's going to make my videos go so much smoother. So, because yeah, once you get like a little hiccup, okay, we know the velocity at that point because the angle's given, but we don't know, and that's going to be the angle right there. So that's going to be phi initial, but now where our ball is, this is going to be phi final, and we don't know that angle, so then we actually have to figure out what the arc length is, of a circle. So, and what I say is radians times radius is something normal, and that normal thing is arc length. It works for radians per second times radius, that's angular velocity times radius, that's something normal, that would be velocity. Same thing for acceleration, radians per second times radius is just acceleration. So the normal thing is arc length, velocity, and acceleration. So radians times radius, we can actually figure out that distance. So that distance is going to be s, and but we need to get it, 35 degrees is our latitude, so 35 times pi divided by 180 is our radians, and then times our radius, and I'm going to store 6.37 times 10 to the 6, store that as alpha r for radius of the Earth. So now we have radians times radius. So now this is the arc length for that. I can't store it as s, but I'm going to store it as n. So now if we wanted to find the arc length at theta final, well, we say radians at theta final times the radius is the arc length. And now we know that the arc length is, well, the arc length that we just found, n, minus 285, because the shot was due north. Okay, so now we have that aspect, and now we can say radians times radius is that arc length, and so we know this, we know the radius, and then we know this has to be in radians, so we can solve for this. And in here, I already said radians times pi divided by 180. No. This is radians in degrees, but then if I multiply by pi divided by 180, this becomes radians. Radians times radius is arc length. But since I already have this as degrees, when I bring this pi 180 over pi over here, this will give me an answer in degrees. Hell yeah. I just like to work in degrees because when we go back to, you don't have to, but just my calculator's in degrees right now. And so when I go throw it into theta, because what the hell did we say? We said the initial velocity for the ball at the tee box at 35 degrees latitude was going to be the circumference of that circle divided by the time of a day. So, and they already say, hey, this radius is RE cosine theta, so that's going to be 2 pi times that radius. That's the circumference at that latitude divided by the time. So the final will be 2 pi radius cosine theta final. You know what I mean? And just in my calculator, I have it as degrees. You wouldn't need to have that. So cool. And then but what is theta final? We just came up with an equation for it. And so you're going to shove this into that. You know, you have to take the cosine of this, and then we're just set. So now we have theta. Now we have velocity final, velocity initial. And so just like that game we were playing, we just want the relative velocity. You know what I mean? Because if I'm going this way at not fast, you know what I mean, and this thing is going hella fast, well, it's just the difference between them. So the velocity, and that's what's happening. You're more towards the North Pole, you're not moving as fast, but then you're shooting at something that's hella moving faster. It's not hella, but you get it. There is a velocity difference, and that's what we want to find. Once we find that velocity difference, just like, well, did we lose the problem? Hell no, because that's going to be in meters per second, and then initially our ball stays in flight alpha t of 8 seconds, and then you can find that distance. You know what I mean? You can find how far that crap is away, and so that's what we're going to do. So basically, we're just going to say alpha t. So our distance that we're off is alpha t in our calculator, the ball in flight, times the relative velocity, and then now it's just plug and chug, because everything here is known. Everything here is known. This initial angle is 35 degrees latitude, and then so this is stored in my calculator as n. That's the only weird thing, is because this time frame was the time for the Earth to spin once in a day, which was 86,000 seconds. And if we want to check on reality, divide by 3,600, yeah, it's basically 24. You know, you can always do check on realities of your numbers. But booyah, is there anything here that's common between? So we have to take v final minus v initial. Well, hell yeah, there's a lot of things that are common. We have 2 pi radius of the Earth. And then you're just doing the differences in the cosines. So now we just have cosine, I'm just going to say of that, minus cosine of 35. All right, cool. And then we do have an s right here that's the same in both. Okay, and then we're just going to multiply it by t. So cool. So now this is the brutal one. So we're going to go alpha s. Okay, cool. That's that. No. This is, holy hell. Alpha n. This is in meters. This is the distance. This is the You know what I mean. And is there a check on reality? What's the circumference of the? Well, we're not going to do that. We're just going to assume that's correct. This is how many meters from the equator up to 35 degrees latitude, minus that 285 meters times 180 divided by pi. Divided by the alpha r radius of the Earth. Cool. So we get 34.997. So we already have a check on reality. We're going to be a little bit less angle. That's what we want. And so now we're going to multiply. So now we have that. Now we have that. Now we're going to shit. Sorry about this. So what am I looking at? So we just found that angle. And now so this is our 34.9, and now we need to take the cosine of that minus the cosine of 35. Cool, so now we have a really small number, and now we're going to multiply by 2, multiply by pi, multiply by the radius of the Earth, and then multiply by alpha t, and then divide by alpha s. And we get a distance of 0.095 meters. Now, I don't know. I'm not even going to check my video if this was right, but it's just like, hey, can we do it faster and get an answer? And so now we're going to divide. I think my answer probably was wrong, you know, because if we divide by 1,000, I'm sorry. multiply by, so if we take this and multiply by 1,000, we have 95 millimeters. And so this seems like this seems like I probably was off. So that's cool, just to do the problem, you know, just in 2 sheets of paper, walk your way through it, get those checks on reality, and you'll probably get there faster. Now, I do the long videos because I just want to actually go from a problem that I have never done and see what the learning process is. And I know I'm going to make mistakes, but still have those checks on reality along the way so I don't make too many mistakes. And then if I do, we're going to celebrate the mistakes we make. So we're going to try to solve for those mistakes as we go through the video. But, you know, I'm just going to post those. None of my videos could have the right answer whatsoever. So now, at this point, I'm going to do the same thing. We're going to go to the internet and see how... Cause what the hell is 95 millimeters? That's about 100 millimeters, which is about 4 inches. So now this makes so much sense. We are 4 inches off. If here's a hole, and as I recall, a hole was like 3 golf balls could fit in a hole. And what the hell is a golf ball? It's a little over an inch, 50. So like I thought a hole was like 150 millimeters. And if we were dead on. Yeah, no, we're going to do that. I'm going to get the dimensions of a hole, and we just missed. You know what I mean? So, but anyway, catch you on the flip side. Alright, hell yeah. So we're back, and we have a hole dimension. So a hole is 108. So if we were going to strike it right in the center, 108 divided by 2, this distance is 54 millimeters. So if we're off by 54 and our ball lands right there, our ball has a dimension of 42.7. So 42.7 divided by 2 is 21. So if we want the ball to be like outside, like fully outside, we're going to have 108 divided by 2 plus that distance of 42.7 divided by 2. So we're going to have that distance plus 54. And so so 75.35, there is absolutely no chance because the ball physically is going to land outside of the hole. And what we have is 95 millimeters. So this is one of those perfect problems where it's just like, hey, like it's at this latitude, if you're shooting and you would have got a hole in one, and if you landed, you know what I mean, that's where you break out your physics book and be like, I was robbed. So yeah, you're going to be 95 millimeters out. And so now we can say that the center of the golf ball is 95 millimeters out. And this is going to be 54. 95 minus 54 is another 41. So 41. And so once we're out here, the diameter of a golf ball, 42.7 divided by 2. So we're going to be 40. So we're 41 minus that. So at 19. You're going to have 19.65 millimeters. So you're going to have the hole 19.6 millimeters, and then your ball. So that distance is going to be 19.6 millimeters, which divided by 25.4 is 3/4 of an inch. So you're going to have your in American, you know what I mean, 3/4 of an inch, and then your 4-inch hole. So that's how much you were off because of this effect. Now this problem sucks because I think from that perspective, it's like Coriolis effect. Well, isn't the wind going at the same speed of the Earth? Sure. But in this case, they're saying wind resistance is negligible. So it's the same thing as being in a vacuum. You fly from here to New Zealand, the Earth rotates underneath you. You shoot a gun from the North Pole, you know, south, the Earth is rotating underneath you. So if you were able to shoot a gun there, the time it got to here, this location already traveled over there. So I think if you consider it in a vacuum, but yeah, you definitely have to negate wind resistance, because the second wind resistance does come into play, and you're hitting those chunks of earth that are shearing that column of air, you know what I mean? That's going to put a if that resistance of going through those layers pulls the ball with it into a rotation, You know what I mean? Because that's what Coriolis effect also does. Is like that column's moving faster and it's shearing up against this column, and then so you get eddies. If you're like in a river, you know, you have a river going this way and then water not moving. Well, now you're going to have swirling vortex on that. So hell yeah. But I have no idea if this is the same answer I got in that 4-hour problem. But, you know what I mean, pen drop for being able to do these things. But, you know, not pen drop because I already did it. And it's just like, but even some of the hard ones, it's like, could you do it again? And the crap thing about this one was you have to kind of figure out what radians are. You know what I mean? You need to know that radians times radius is arc length. And that gives you distance in normal units of meters. If your radius is in meters and your angle is in radians, there you go. And what the hell is a radian? Well, let's finish the video with that. You have a circle that has 360 degrees. Here's your radius. If we measure that radius with a string, cut it to length, and then drape it along the circle, we'll get to there. And then and you would have to drape about 6 of them all the way around the circle. Actually, 6.28. So we're saying that that is a radian of 1. You know what I mean? Draping the radius there, so there you go. And you're going to have 2 pi of those in 300. Alright, hell yeah. My camera kind of shut out, but so there you go. If you drape these radiuses around a circle, it would take 6.28 of them, which is 2 pi. So and there you go. And then that's what we're calling that angle of draping one radius is 1 radian. So there's a radian, there's a radian, you get a radian. And so you have this symmetry, I mean you have this identity that 360 degrees is 2 pi radians. You know what I mean? So if I say, oh, I only have 30 degrees, well, you know what I mean? I have proportionally this much less, so it looks like I'm going to have 2 pi maybe divided by 10. You know, this looks like 10 less, and then so you set it up, be like, well, how do you find this? You go 30 degrees, well, we know that 360 degrees is 2 pi, and then so the degrees cancel, and then you're left with 2 pi radians. So we go 2 pi divided by 360 times 30, and we get 0.5. So, which was pretty close to 2 pi divided by 10. You know what I mean? So there you go. We're going to end it at that. And I hope this answer is right. You know what I mean? I did it again. I could probably try to do it a different way. But I'm going to call it on that. And thanks for joining me. And that's a video.